Hello, everyone, and welcome back to week 2. This week we're going to be studying gas laws. So, I'd like you to take a look here at the PowerPoint presentation on gas laws with me today. And we're going to do a brief review of states of matter before we get into gases and gas laws themselves. So, for states of matter, we need to remember our three states: solids, liquids, and gases. And we've got our progression of energy here. As you can see in the graphic, the solid, as we're adding energy to it, it's going to progress to a liquid because those intermolecular forces are weakening due to the kinetic energy being provided by the heat. As we continue to add, those intermolecular forces in the liquid are then broken and we change to a gas. And on the bottom, you can see the opposite happening with the removal of energy. So gases condense into liquids, and then liquids freeze into solids. So our three main properties then for states of matter are the intermolecular forces, as mentioned, the kinetic energy or the energy of motion, and then these impact the density. As you can see, our solid is the most dense and packed together nice and tight. Liquids start to space a little, and then gases spread out independent from one another. So to review some of our states of matter, as far as the shape and volume are concerned, it's important to remember that with solids, the shape is constant. It has its own volume. It's not defined by its container, but it's its own volume due to the substance being in the solid state. It therefore also has a constant volume as well. So we have high intermolecular forces, as it says here in the red, that hold this solid together in a constant volume and a constant shape. Liquids, on the other hand, are going to have medium forces. We're loosening up the intermolecular forces a little bit by adding energy, but those particles are not going to have their own shape. The shape of a liquid is defined by the container it's in with the parameters that that container gives it. It does, however, have constant volume. So the volume is not changing for a liquid as it's in the liquid state. It does stay a constant volume. With gases, we have movement that is rapid, it's random. We have elastic collisions, as we've looked at with the kinetic molecular theory. So no forces or intermolecular forces to be specific, and these particles of gas are not attracted to each other because there's no intermolecular force to attract them. So we can see we have random movement. Every direction is indicated by these arrows, and they collide with each other. They collide with the sides of the container, and we have bouncing and jostling around of the particles going on. So they do bounce off everything, the walls and each other. There's a lot of kinetic energy within these because they're typically at higher temperatures and there's no intermolecular forces present to hold them close together. They do have a very low density, and they are very spread out because of that low density. Measuring gases is done primarily using the unit moles. Now, you might remember from chemistry A, the unit of the mole that we talked about. It's a way of quantifying matter for us in chemistry, since we're looking at matter in chemistry and the physical makeup of substances. Moles are a unit that allow us to quantify the number of particles making up matter. So within gas laws, this amount or moles is going to be represented by the variable n as a lowercase n there in parentheses on the slide. Volume is represented with a capital V. Volume is, of course, the size of the container holding the gas, right? So gas is going to fill up whatever space you give it, whether it's very small or very large. And then temperature, we are going to be focusing on the Kelvin scale of temperature. So we're looking at how much kinetic energy is present within the particles and their movement, and how they're colliding. So the temperature helps us explain the collisions. It will also help us explain this next one, which is pressure. So temperature affects pressure. The more temperature or the higher the temperature increases, the more collisions we have with the side of the container for a gas because they're going to move faster. So the faster they move, the more they're bouncing around and colliding with the walls of the container. So pressure, or P, is measurement of how often those particles are bouncing off the container. In order to measure pressure and further understand pressure, we want to look at a couple parameters for pressure. So pressure is a force, right? Because they're colliding, so it's exerting some sort of force on another particle or on the wall of the container. It's how fast the particles are hitting or how hard the particles are hitting the container or each other, and how many are hitting at one time. So those two factors will impact pressure with inside a container. And you'll get a chance to practice and look at this later this week. The air around us even has a pressure, atmospheric pressure, right? So atmospheric pressure is measured with an instrument called a barometer. And barometer measurements are used to predict the weather. And you may have heard a weather person talk about this if you've watched a weather forecast. Sometimes they'll say the barometer's on the rise or the mercury's falling. Um, Barometers used to use mercury. So mercury would go up or down in the column, which is called a barometer, the instrument used to measure atmospheric pressure or how much force is pushing down on this pan of mercury. So at typical sea level, right? So if we're standing at the beach next to the ocean, 1 atmosphere of pressure is what's typical at sea level. Now that changes as you move away from sea level because as you go up in elevation, you have less atmosphere pushing down on you. So if you go to Denver, for example, the atmospheric pressure in Denver is going to be lower or less than the atmospheric pressure, say, on the Gulf Coast. So takeaway, remember the higher you go in elevation, the lower the pressure gets. The other aspect that we want to look at is temperature. Okay. And temperature, we've talked about, measures kinetic energy. Again, energy of motion or how the particles of gases, in this case, are moving, right? Because this chapter is specifically on gases. So we're looking at how does temperature impact gas behavior and gas movement. In gases, we need to scale our measure to an absolute value to measure the absolute kinetic energy. We don't want an average, we'd like an absolute kinetic energy. So this is why we use the Kelvin scale after Lord Kelvin. So to get from our typical temperature scale of Celsius, we have to add 273 to get to Kelvin units. Okay, so just a note on Kelvin temperature, it is Kelvin units, not degrees Kelvin. Kelvin does not use degrees on the scale. Celsius uses degrees. Kelvin is in units. Okay, so just a clarification point as we move forward and you begin working with the Kelvin units of temperature. So standard conditions are important to us in looking at gas laws. Standard conditions can be really specific and kind of help us in generalizing. But we know that in everyday life or in a classroom or in our home or wherever we're at looking at gases, these gases or materials are going to have their own temperature and pressure depending on the location that they're at. So we need a set of standards to help us kind of standardize that across the board to explain behavior, to calculate amounts like moles, and to understand these in general, to have a standard. So that standard comes in an acronym or letters called STP, which stands for standard temperature and pressure. So standard pressure is 1 atmosphere. As we mentioned, at sea level, the atmospheric pressure pushing down is typically 1 atm or 1 atmosphere pressure. Our standard temperature for a gas is going to be 0 degrees Celsius, which is the freezing point of water, remember. Or if we convert that and add Kelvin units to convert it into Kelvin, our value for Kelvin units is 273 for the freezing point of water. So 1 atmosphere pressure, and then temperature is 273 Kelvin or 0 degrees Celsius. So to start looking at the relationships that these different variables have within gas laws, we first of all want to look at the relationship between pressure and volume. Okay, an inverse relationship between pressure and volume means that as pressure goes up or as it's high, here on our first diagram, the volume is low. Notice the piston in the cylinder is compressing that gas and it's therefore driving up the number of collisions of the gas on the side of the container. So you see the pressure gauge climbing to a higher number on our imaginary scale there. If we pull the piston back out and allow the gas to take up more space, it reduces the number of collisions with that container or the walls of the container. And you see the needle comes back down or drops for our pressure reading. So as the volume comes down, the pressure goes up. Whereas the volume goes up and it has more room, the pressure comes down. So it's an inverse relationship. Okay. In a flexible container, like if you had a balloon, for example, that's stretchy, the pressure inside and out is always the same because it can change due to that flexibility. So the volume changes to keep the pressure equal. Our next relationship deals with volume and temperature. Volume and temperature have a direct relationship. And you can see as volume goes down, the temperature goes down. Okay, because a direct relationship, they both go the same way. Volume goes down, temperature goes down. If volume goes up, temperature will go up. They both go the same direction, and you can see that represented here on our graphic or our image on the slide. And our third relationship, we're looking at pressure and temperature. Okay, so changing the temperature, as we mentioned before, is going to change the kinetic energy or the speed at which particles move. So if we increase that kinetic energy or increase the temperature, there's going to be more collisions of those gas particles. So the image on the right has boiling water, and you can see the streaks behind are gas particles moving around. right? So the pressure value there is 1.37 atmospheres, higher than normal atmospheric pressure because we've increased the amount of movement, therefore increasing the number of collisions. If, however, we place it in an ice bath and we cool those particles down in an ice bath, those particles slow their movement, right? And we've now dropped our pressure to standard atmospheric pressure, or 1 atm. So pressure and temperature, again, are directly proportional or directly related. They either both go up or they both go down. Okay. So we can take these three different parameters, volume, pressure, and temperature, and we can put these three together and we can have two sets of conditions, which we call the combined gas law. By combining volume, pressure, and temperature from one set of conditions to volume, pressure, and temperature in another set, it gives us a combined gas law that then we can then compare two sets. Like we looked at on the previous image, those two flasks had gas at a cold temperature in an ice bath and gas in a flask at a hot temperature with boiling water. So we can compare those two conditions with this particular equation, the combined gas law. We do need to make sure when we use the combined gas law, however, that our temperature is in Kelvin units, okay? Because we need the absolute value of their motion, not an average. So if we do not have all three parameters or variables, we can cross out whatever doesn't change, and we can use that to solve for the unknown. Our final equation that we want to look at today is PV equal to nRT, called the ideal gas equation. This equation brings in the amount of moles, or our quantity of gas that's present, so we can quantify the gas present in a container or in an experiment for this equation. So we have pressure and volume multiplied together is going to equal the number of moles times the gas law constant R times temperature, which is going to be in Kelvin units. So P needs to be in atmospheres for our R value. T needs to be in Kelvin for temperature. And then V is either going to be in milliliters or liters. So the value for our R, or gas constant, depending on the unit of volume, if your volume's in milliliters, your gas law constant, or R value, is going to be 82.1. If, however, you are using liters, your R constant is going to be 0.0821. 0.0821 for volume in liters. So for real gases that are not under ideal conditions, um, we don't follow the kinetic molecular theory all the time. The ideal gas law follows the kinetic molecular theory and everything that it says. So, for example, if you look at the graphic below, um, the ideal gas with no intermolecular force travels in straight paths. A real gas with intermolecular forces travels a curved path. Okay, so that's one factor that could change as a result. Um, so they're not always at very high pressure or very low temperatures, and they can start acting like liquids where they tend to clump together and stick. Okay. So that is our overview of gas laws for today. We'll be talking more about them on our next lesson, and we'll also get into some applications so you can start interacting with some of these parameters like volume, and pressure and temperature. And you can look at those and how those change when you change each one, how that impacts another constant. So we'll look forward to talking to you in our next lesson and looking at the applications.